I did a little rearranging of the setup here. I put both the turbo and the fusor itself on this optical plate that I had sitting over here. This is still a huge mess, but this allows me to mount some optical equipment and stuff for filming. I was playing around with a 90-degree reflection for being able to film the plasma without having the camera, the CCD, basically exposed directly to potential x-rays and stuff. And I got super lucky on eBay recently, and I got this really nice, well, really nice for me at least. I'm sure there's labs playing around with much nicer power supplies, but this thing, they call it a 600 watt equivalent, but I don't think it can actually do the full power at max settings. But it's basically a 500 watt power supply, high voltage power supply, that allows you to control amperage and voltage, and it goes from, fully controllable from 0 to 30 kV and from 0 to 25 milliamps. So this thing is basically by itself good enough for me to be able to do fusion. I still want to build my own supply. I think I'm gonna aim for about 40 kV and 30 milliamps to be able to really push the system and see what the limits are for a small setup like this. But yeah, for now, this is gonna be great for me to get a feel for how the plasma behaves, along with do some measurements, because once I start pushing past about 15 kV, you start getting a good amount of x-ray generation, and so I'm gonna use this to test out how bad the x-rays are, and basically shield the system with some lead sheeting. And as you can, I already played with this a bit and realized some definite mistakes that I made. First of all, being the grid construction, I'm gonna have to redo for sure, because I used nickel because it was so easy to spot weld, and that was definitely a mistake. It sputters really badly. I don't know how easy it's gonna be to see. Yeah, so see how that viewport is reflecting my hand so well? It's because the inside has a thin layer of nickel on it, and it's basically turning this thing into a mirror. And I'm pretty sure the other viewport did the same thing. Yep. So that's problem number one. I'm gonna have to clean those up when I take this apart. The other issue with the nickel is that it has a relatively low melting temperature, which makes it not great for prolonged actual fusion operations, because I'm going to be dumping a few hundred watts of power into this thing, and I was already seeing it get red hot during preliminary testing, so it's just not going to be a good idea to keep using the nickel grid. So I'm gonna, it's not a good idea to keep using the nickel grid for actual fusion runs. I'm going to continue using it for now for some x-ray experiments, to just get a feel for how the system is putting x-rays out, and then also just to do some plasma dynamic experiments with different gases and whatnot. But yeah, I'm gonna have to swap the grid out. I think I'm gonna try some different construction methods, because ultimately tungsten is by far the best, it seems, to use for this. Another thing though, vacuum, yesterday after playing with this thing, I'm already down into the -7s, so it is holding really good vacuum. Well, I'm going to need to remove the high voltage feed through to get at the grid here to replace the grid. I think I'm going to try and make a simple kind of like thin gauge tungsten grid. And while I'm at it, I'm going to remove this viewport and see if I can clean the inside up of the deposited nickel to get the transparency back. And then I think I'm also, for the time being, for these initial experiments, especially with trying to nail down a grid shape that I like and material, I'm going to swap this conflat mounted feed through for a KF quick connect feed through, mounted feed through that uses a fitting like this, and that way I'm not burning through these copper gaskets every time I want to swap a grid out. Here's what the viewport looks like from the inside. You can see that mirror finish on it. Yeah, definitely got a good bit of nickel deposited. Here's what the grid looks like inside after having been used. Let me turn this flashlight on, get a better look in there. Looks pretty good. Seems like the 20 centimeter size, diameter size is gonna work pretty well for the spherical grid. I might shrink it down a little bit. We will see. I ended up using the Dremel with a polishing paste to clean up the window. It's a 2.5 micron diamond polishing paste. It's for getting like a mirror finish on metals and whatnot. I think you can use it for stone as well. Pretty sure you can. But anyway, that did the trick. It worked really well. Made it really easy to clean this up. Didn't leave any, obvious scratches or anything like that. So I'm definitely going to be using this in the future, just because it made really quick work of that. And I bet it will also work for things like tungsten and molybdenum and whatever else I use for my grids that end up getting sputtered on here. Here's the electrode and grid. Yeah, so you can see here, I'm gonna pop this connection off. Basically where the copper connector here, or maybe it's brass, I'm not sure, but it started getting kind of coated in nickel. It's not that coppery color anymore. And here, let me grab them. Here's what they look like by comparison, before being coated. You can definitely see a bit of a color difference here. So this is fresh connector, and then this is the one that's been coated with sputtered nickel, basically from this grid. And yeah, the grid looks fine. Pretty much looks the same as how it started. It's very kind of shoddy craftsmanship for sure, but it held up more or less. The sputtering was kind of a shame, but I should have known better. I was just trying to kind of rush to get some kind of plasma going in here, and yeah, nickel is really not a great material to use. It's fantastic to spot weld with. I mean, I basically didn't have to try at all, nothing special to spot weld it. But yeah, it's just not gonna work. So now what I'm going to do, so I'm going to swap this feed through for this one here on this quick connect fitting. Basically same voltage rating and all that, but this one's on a quick connect fitting, so you technically can't get, you know, as low of a vacuum, but for these tests this will be just fine. And really for operating a fusor, you know, you don't need to maintain, like, really in operational mode you're somewhere between, I don't know, let's say 5 and 30 millitorr depending on the setup. So this fitting is totally fine for that. It's only if you're trying to really pull hard vacuum in a system that you want to avoid using these types of fittings, and you just want to stick to the copper gasket fittings. Here's the new adapter installed on the chamber for this style of fitting with the feed through. So this will allow me to quickly, you know, install the feed through and take it off to swap out these grids. So it just goes right on. This grid is a little bit too big in diameter, I think, for this chamber, but I kind of just want to see what it will look like as far as the plasma goes. And that's pretty much it for what you have to do to swap this feed through out now, which is pretty nice. Will make this a lot easier to troubleshoot the grids, because I think that's a problem point for me currently for this. And here's what that shaker ball grid looks like in there. Yeah, I think it's gonna be way too big for this chamber, unfortunately, but that's all right. It should still be fun to play with. We got the new grid in there. It's way too big for sure. This isn't gonna really work, but it's kind of fun to play with. And yeah, you can see it, you know, way better now through that viewport. But here, I'll show you what I mean of it being too big. It basically is too close to the walls, and so it starts kind of shorting out here and there. That looks like a strobe light, but yeah, you see those little sparks? That's basically stuff being blasted off of the grid, probably some organics or something stuck to it, but that flashing means that it's arcing over and over again to the wall, so there's just not enough standoff distance for it to sort of continuously blow discharge. It's pretty close though, and I have it at about 10 millitorr right now of pressure, so it's doing all right. The chamber is fine for sure. It's just that I need a smaller grid in there, pretty much. But the other thing that I wanted to show with this that I think is a lot more interesting is some x-rays. And I'm only going to take it up to about 17 kV, as I found to be a good spot, where you basically see, you know, I'm using this radio code gamma spectrometer to pick up x-rays, but you see a count increase right outside the window, and then it starts dropping off very quickly as you move away. So this is, you know, relatively safe for me to do. I wouldn't recommend you know, doing this long term and whatnot. And I do have some lead shielding that I'm going to use to set up around this thing, because once you start going up in that voltage, the x-rays become harder and harder, they penetrate farther, they have more energy, then it starts becoming a legitimate safety issue, which is why I'm going to shield for that. And I'm also thinking about putting in kind of a longer one of these bellows tubes, hoses, to get the turbo away, so that way I have more working space here for like activation experiments and things like that in the future. I've reset my spectrum accumulation here, and what we want to see is, you know, I've zoomed in on the spectrum, and this whole range is up to about 74 keV, and we want to see right down here in the lower energy region a hump start to grow, indicating the pulses from these lower energy x-rays. So I'm gonna slowly increase the voltage, and the x-rays are being generated from, you know, electron braking around a nucleus. Basically, you know, electrons are being accelerated from the grid out towards the chamber wall, and then the chamber wall atoms, because the nucleus is positively charged, the electron as it approaches the nucleus will sort of get you know, deflected in its orbit, and that deflection causes a deceleration, and the energy loss of that deceleration gets released by a photon, via a photon, and that's your X-ray radiation essentially. I'm sure that's not a totally great explanation, but I think it's good enough. So just for example's sake, here we are at right at 15 kV, 15 kilovolts, and I can put my gamma spec right up to the window. It might be picking up a little bit, but not much. Yeah, not really anything. So that's at 15. And now I'm just gonna get the spectrum back open. So now if I bump it up just 2 kilovolts to 17, what we'll see is a pretty major difference. So there goes the count. It's starting to increase in front of the window quite a bit. Nothing too crazy, but, and look at this. Right down there, the spectrum is starting to grow where that peak is. And it's going to be a relatively kind of broad peak, because that braking radiation is sort of a continuous thing in terms of the photon energy. But yeah, look at that. That's pretty cool that you can just pick that right up. And the other thing here is just to demonstrate, so I'm right at the window. I've got, you know, about 11 counts per second. So now as I slowly move away, now I'm about 4 inches from the window, maybe 6 to 7 inches. See, we're starting to quickly drop back off here. Yeah, and we're basically now back to background, you know, a little over a foot away from the window. So it drops off pretty quickly at this energy level. And the other thing too is, you know, the window lets the x-rays through pretty well. But now if I go to the stainless steel, see there's not really much of very much above background. There's still a little bit, and this hose might be, I thought with the hose being thinner it might let through more. What about the ceramic? Yeah. And then I've got this other window back here that should also be letting through quite a bit. Maybe. Maybe not. Probably because of all the nickel coating on it. I bet that's enough to provide some extra shielding, but you can see the count go up just a tiny bit. And then again on this clear window here, we've got a larger count rate. So those are x-rays, which I think is pretty neat. It's just amazing that you can kind of do this at home. And there's the spectrum. There's that peak that grew down on the lower end. Here's the full spectrum. You know, this thing goes out to 3 MeV. It's pretty, you know, it's way higher than anything that I'm gonna put out here. But there's our little x-ray peak right there. And on the lower range, you know, this gamma spec isn't really gonna give super accurate results in terms of the exact energy at which that photon is coming out. But the point is that we can see it happening here. Yeah, so that's where the fusor stands as of today. And this power supply has been quite the lucky find. It's going to allow me to do very interesting experiments quickly and start iterating through some grid designs and shielding and all that fun stuff to make this thing work properly and safely. Alright, I'm gonna let this pump down overnight, see where we can get to with the vacuum, with that fitting on there. Close off my argon here. That's what I don't know if I mentioned it, but argon is what I'm using right now just for the atmosphere in there for these plasma experiments. And the X-ray experiment, I don't know if it's not really an experiment, but demonstration, I suppose. Alright, and looks like that fitting is doing pretty well. I mean, we're already in the -6 range, which is pretty good. Turn the light on here. Yeah, and then here's the old nickel grid wire, which I will not be using again, but I think I'm gonna make an effort to keep all these grids as I iterate through them, and just it'll be fun to keep all the failures. Hopefully there's a lot more learning.